Hey everyone, welcome back. I hope you're all doing great. In this video, we'll walk through a comprehensive example, step by step. The project information is provided in the table, which includes activity names, their durations, and their predecessors. Based on this, we need to complete the following tasks. First, we'll develop the precedence diagram for the project. Second, we'll calculate key scheduling times, including early start, early finish, late finish, and total float for each activity in the network. Third, we'll identify the critical activities in the schedule. And finally, we'll determine the critical paths in the network. All right, let's dive in. First, we'll begin with the start milestone as our initial activity. The next activity in our sequence is activity A, which takes 1 day to complete. As shown in the table, it doesn't have any predecessors, so we can place it directly in our network, following the start milestone. Moving on, we have activity B, which has a duration of 3 days and follows activity A as its predecessor. Since the specific dependency type isn't mentioned, we'll assume a finish to start, FS logic. With that assumption, we can now add activity B to our network like this. Next, let's take a look at activity C. It also has a 3-day duration and is preceded by activity B. However, in this case, the relationship is an SS, start-to-start dependency, with a 2-day lag. Remember, for SS logic, we draw an arrow from the start of the predecessor, activity B, to the start of the successor, activity C. Now, let's move on to activity D, which has a 3-day duration and is preceded by activity A. Since no specific dependency type is given, we'll assume a finish to start, FS logic, and add it accordingly. Next up is activity E, which follows activity B. Again, without a specific dependency type mentioned, we assume finish to start, the FS logic, and place it in the network. Now, let's talk about activity F. This activity has 2 predecessors. The first is activity C, which follows a finish to start, FS logic. The second is activity E, but this one follows a finish to finish, FF dependency, with a 3-day lag. So, when adding activity F to our network, we connect the finish of activity C to the start of activity F, and the finish of activity E to the finish of activity F, making sure to include the 3-day lag in the FF logic from E to F. Alright, moving along, we have activity G, which follows activity D using a start-to-start SS logic. Then we have activity H following F, via a finish to start FS logic. Now, let's take a look at activity I. This one takes 7 days and has 2 predecessors. The first is activity D, which follows an FS logic with a 2-day lag. The second is activity G, which also follows an FS logic but with a 4-day lag. Next, we have activity J, which also takes 7 days to complete. It is preceded by activity H through an SS logic with a 2-day lag. It also follows activity I via a finish to start dependency. Finally, we need to add the finish milestone. To do this, we connect all activities without successors to the start of the finish milestone, and that's it. The precedence diagram method network is now fully completed. All right, let's move on to item number 2, figuring out activity times and total float. To do this, we'll need to go through both a forward pass and a backward pass. If you're not too familiar with how these calculations work, I'd recommend checking out the previous videos where we go over forward and backward passes in detail, as well as how to calculate total float. But in this video, I'll go ahead and review the final solution. So let's take a look at what we've got in our network. First, the start milestone always has 0 values for time and float because it's just the starting point of the project. It doesn't have any duration. Now, if we jump to the finish milestone, we see that both its early and late times are 29, which tells us that the total project duration is 29 days. And since this marks the end of the project, its total float is always 0. You can't move it unless the entire project gets extended. Alright, now let's break down a few other activities. Take activity A, for example. Its early start is 0, and its late start is also 0, which means the start of this activity is critical. What about its finish? Well, since its early finish and late finish are the same, that means its finish is also critical. So, activity A is fully critical, and that's why its total float is 0, which you'll see in the middle top box. Now, let's check out activity B. If we look at the start side, its early start is at day 1, but its late start is at day 7. That means we've got some flexibility here. We can delay its start by up to 6 days, from day 1 to day 7, without affecting the overall project timeline. Now, if we check the finish side, the early finish is at day 4, while the late finish is at day 10, which means the finish of activity B also has a 6-day float, the same as the start float. As you can notice here, these also match the total float, which is 6 days. So, here's something to keep in mind. Total float is basically the maximum amount of time an activity can be delayed before it starts impacting the project's completion. So, start float and finish float can never be bigger than the total float. They'll always be equal to or less than it. Alright, Now let's take a look at the network and identify both critical activities and critical paths. First, we'll identify the fully critical activities, which are the ones with zero total float. Based on the network, the fully critical activities are A, G, I, and J. Next, let's check for partially critical activities. These are activities that are critical either at their start or finish, but not both. The only partially critical activity here is activity D. It's critical at the start because its early start and late start are the same, but its finish is flexible. Its finish can be delayed from day 4 to day 13 without affecting the overall project timeline. Now, let's determine how many critical paths exist in this network. Remember, a critical path is a sequence of critical activities, either fully or partially critical, that has a total duration that matches the project duration. To find the critical path, let's start from the start milestone. It is followed by activity A, which has a 1-day duration. This is fully critical, so we include it in the path. From activity A, we have 2 possible paths, one leading to activity D and the other to activity B. Since activity D is critical at the start, but activity B is not, so we follow the start of activity D. From the start of activity D, we move to activity G, which takes 10 days to complete. This activity is fully critical, so the whole activity could be part of a critical path. Then, we go from activity G to activity I, which has a duration of 7 days. It is also fully critical, so we add it to the path. Don't forget the 4-day lag between G and I. That time is also part of the path. After that, we continue from activity I to activity J, 7 days, another fully critical activity. Finally, we reach the finish milestone, which is always included in a critical path. Now, let's double check that this is a critical path by confirming its total duration. If you forget how to calculate the path length, please check out the previous video. To find the path length, let's add up the durations. 1 day for activity A, 10 days for activity G, a 4-day lag from G to I, 7 days for activity I, and 7 days for activity J. That gives us a total of 29 days, which matches the project duration, confirming that this is indeed a valid critical path. Now, is this the only critical path? Yes, you won't find any other sequence of critical activities that adds up to 29 days, and that's it. We've successfully identified the critical activities and the critical path for this project. Goodbye for now, and we'll see you in the next video.